You know that feeling, right? You've got this awesome, super powerful computer with tons of cores, but your Python script is just, well, chugging along, stubbornly using only one of them. It is such a common bottleneck. Well, today, we're going to crack that problem wide open and show you exactly how to unleash your machine's full power.
And this quote right here, it gets right to the heart of the solution. Stop trying to share one copy of Python. Now, I know that might sound a little weird, maybe even counterintuitive, but trust me, this one idea is the key to absolutely smashing through Python's performance barriers when you're doing heavy-duty work. Let's dig into what that actually means.
So let's meet Timothy. He's a junior dev working on this huge project, the Grandmaster Analysis Engine. It is packed with some seriously heavy calculations, and it is painfully slow. He feels like he's hit a glass ceiling. It doesn't matter how many threads he throws at the problem, his code just doesn't get any faster. And that's when his senior colleague, Margaret, steps in.
Okay, so the main villain in Timothy's story is this thing called the Global Interpreter Lock, or the GIL. To put it simply, the GIL is a basic rule built deep inside Python that says even if you have a bunch of threads ready to work, only one of them can actually run Python code at any single moment. It's a built-in bottleneck for doing things at the same time.
Here's a great way to think about it. Imagine you have a whole team of workers. Those are your threads, all in a room ready to go. But there's only one microphone. That microphone is the GIL. So they all have to take turns speaking. One person works, and everyone else just has to wait. Now, this is totally fine for jobs that involve a lot of waiting around anyway, like fetching data from a website. But for a heavy math problem, it means you're not really doing work in parallel at all.
So the big question is, how do we give everyone a microphone? Well, Margaret shows Timothy that the solution isn't about trying to get more efficient in that one crowded room. It's about giving everyone their own room.
And this is the big aha moment. Instead of using threads, which are kind of like roommates sharing one apartment, Margaret suggests using processes. A process is a completely separate, independent copy of the Python program. Each one gets its own memory, its own room, and most importantly, its own microphone, its own GIL. Suddenly, we're not sharing anymore, we're duplicating. So, Timothy gets to work. He rewrites his code using Python's multi-processing module, setting it up to run his calculations across 4 separate processes. He hits enter, and for the very first time, he hears his laptop's fan just roar to life. Something is definitely different this time.
He quickly pulls up his activity monitor, and this is the beautiful sight he sees. 4 distinct Python processes, and every single one of them is absolutely maxed out at 100% CPU. See, it's not one worker taking turns anymore. This is like having 4 specialists in 4 separate offices all going full throttle at the exact same time.
This is that breakthrough. That glass ceiling, it's completely shattered. By giving each worker its own independent copy of Python, Timothy has finally achieved what we call true parallelism. The work is really, finally, happening all at once.
But, as Margaret is quick to point out, all this power comes with a price. This independence isn't free. There's some really important trade-offs you have to understand when you make the jump to multiprocessing.
Since each process is a full, fresh copy of your program, it has its own completely isolated memory. It helps to think of them as living in their own parallel universes. If you change a variable in process 1, process 2 has absolutely no idea that happened. It's still working with its own separate, untouched copy of that data.
And that right there is the fundamental trade-off. You're swapping the convenience of easily shared data, which you get with threads, for the raw, unadulterated speed of true parallelism that you get with processes. You can't just change some global variable and expect another process to see it. It's just not going to work.
To make this choice crystal clear, Margaret draws up a little cheat sheet for Timothy. She frames the whole thing as a choice between lightweight roommates, which are threads, and independent specialists, which are processes.
So let's break this cheat sheet down. Threads, our roommates, share memory like it's one big whiteboard, but they're all stuck with that one microphone because of the GIL. This makes them great for I/O-bound tasks, things with a lot of waiting. Then you have processes, our specialists. They work in their own isolated offices with their own memory and their own microphone. This is absolutely perfect for CPU-bound work. The final trade-off? Threads are lightweight, they're cheap to create. Processes are heavyweight, they take up more resources to get started.
Finally, Margaret gives Timothy 3 rules. These are non-negotiable. If you're going to use the power of multiprocessing, you have to follow these specialists' rules to do it safely and effectively.
Okay, rule 1 is the guard. You must wrap your main code in an if name equals main block. If you don't, you can get stuck in a crazy loop, spawning infinite processes and crashing your entire machine. Rule 2, the limit. Be smart about this. Use multiprocessing.cpu count to see how many cores your computer actually has. You don't want to spin up 1,000 processes when you only have 8 cores. And finally, rule 3, the wall. Always remember that memory is isolated. Global variables are not shared, period.
So, the next time your Python code is just grinding away on some heavy calculations, you can ask yourself, do I need a roommate who's good at waiting around? Or do I need a team of independent specialists to just get in there and crush the job? Now you know exactly how to choose.